Welcome to A History of Python Versions and Features. This is a coding conversation course. My name is Christopher Trudeau.
And my name is Christopher Bailey.
And we'll be taking you on a little journey through the Python language over the last 35 years, highlighting what features got added to the language when and how some of them work. Although this course is formatted as a language history lesson, it also works as an overview of a whole load of features. Some you might know and some you might not. In this course, you'll learn about context managers and the with keyword, default dict, Python 2 to 3 transition, yield from, unit tests mock, enums, pathlib, fstrings, data classes, the Walrus operator, match case statements, tstrings, and more. For the most part, the code in this course was tested using Python 3.13.5. Some of the older stuff meant I had to install an ancient interpreter, and at the end you'll see some of the newer stuff coming out in the fall of 2025 with Python 3.14.
So Python was created by Guido van Rossum, and this is the announcement that Guido sent out on comp.lang.misc in 1994. Tired of deciphering the Perl code you wrote last week? Frustrated with bourne shell syntax? Spent too much time staring at core dumps lately? Maybe you should try Python, the next generation object-oriented scripting and prototyping language with a readable syntax. Python has been used by hundreds of happy users all over the world during the past 3 years and is now ready for prime time. Python 1.0, 1994. Basic function syntax was the same as you're used to. It included a REPL, that's a read, evaluate, print loop, if you're not familiar with that. It included exceptions, but they were very much bare bone at the time. No classes yet, and a fairly comprehensive standard library, which is still one of the features that people enjoy about Python. So we're going to dig into Python 2.0, which was introduced in 2000. They've added Unicode support through the U prefix, added one of many people's favorite features of Python, which is the list comprehensions, and added methods for strings. Python 2.1, introduced in April of 2001, added nested variable scopes. So if you're familiar with the scopes in Python and the idea of local enclosing global and built-in scopes, that's where this is starting to be introduced. And then also rich comparisons were added. This includes the special methods of the dunder LT, which is less than dunder LE, EQ, and so forth. With the introduction of Python 2.2 in December of 2001, the new style of classes was introduced. Integer division using // and generators were introduced. Python 2.3, a couple years later in July of 2003, added the Boolean data type and added sets as a data type in a module. Along with that, added the enumerate function.
To learn more about some of the features covered in this course, there will be deep dive links throughout. All of these are available in the notes below the course. The first set of links I want to talk about are the official What's New in Python docs. Every release of Python comes with one, and it includes loads of information on what is in the release. The format of the link is the same for each release. So whatever version you want to see, just substitute the number in the end part of the URL. You'll notice there's also a 3 earlier in the URL, even for 2.x releases. This got added when Python transitioned to version 3 to differentiate it from the older docs. But they did port the what's new of older versions to the new doc format. So you can just leave that first 3 alone and edit the version to find the one you're looking for. In addition to outside links, there is also tons of content at RealPython. If you'd like to learn more about rich comparisons and the dunder methods that achieve them, this course and article has loads of info. Or if you'd like to learn about list comprehensions that got added way back in 2.0, this course and tutorial will teach you all about them. They're a good tool to know as they often outperform their for loop equivalents.
Continuing more about Python 2, Python 2.4 was introduced in November of 2004, and the set moved from being a module that was imported to as a native data type. Function decorators were added, and the reversed function was added to allow the reversing of iterables. There's lots more at Real Python here for you if you'd like to learn about Python decorators. This is one of the first courses I did for Real Python, and I learned a ton, and I think you'll learn a ton from it. And there's a much more detailed tutorial by Garon Ayala that goes into a lot more examples that you can kind of dive much deeper into.
As we progress along, that little guitar symbol will show you courses that Christopher Bailey himself did.
And if you want to learn more about using sets in Python, we have a written tutorial and a course on it.
In the next lesson, we'll continue on with Python 2.5, covering context managers and the with keyword, as well as talking about the default dict from collections. In the previous lesson, we covered the early history of Python leading up to the 2.4 release. This lesson covers Python 2.5, the with keyword through context managers, and default dict from collections. Python 2.5 saw the introduction of the functools module. This is kind of an interesting point in the language. Python started out as a traditional procedural scripting language. Then it added some object-oriented concepts, several times over, and here it added tools for functional programming. Functional programming uses a methodology where you compose functions together to perform actions. It's more declarative than procedural programming. This isn't really Python's strong suit, and in fact, there are languages designed around this paradigm. But functional programming is good with certain kinds of algorithms, and so Python mixing it in gives you a little more choice. The any and all functions fit this concept well, the first returning true if any item in an iterable is true, and the second returning true when all items in an iterable are true. The min and max functions existed already, but 2.5 added the key argument, allowing you to specify how to determine if something is min or max. This is particularly useful if you're trying to get the min or max of a series of objects. You can use the key to access an attribute within those objects. 2.5 also introduced context managers, which you use through the new with keyword. It also added the default dict class, which is an extension to dict that automatically sets a key to a default value. All right, enough of this death by PowerPoint approach. Let's head to the REPL and dig into two of these features. First, context managers with the with keyword, and then the handy little tool, default dict. To better understand with, I'll first explain what it looks like without. See what I did there? Say you want to read a file. You call open and get back a file handle. Then maybe use readlines to get at its content. My file had the numbers 1, 2, and 3 on separate lines, and readlines returns those as a list of strings corresponding to each line in the file. The closed attribute tells you whether a file handle is open or closed. Since I haven't closed it yet, it's returning false. Closing files is important. File handles take up resources. Not only do they cost memory, but most operating systems restrict the number of handles that you can have open at one time. For our simple example here, it doesn't matter, but lots of interfaces on your computer use this same file handle mechanism. If your program deals with sockets and lots of things are connected to your code, each connection gets its own file handle. If you don't clean up after yourself, your program might eventually crash. And that cleanup is as simple as calling the close method. Great, so now it's closed. Every open should be paired with a close. It's easy to create a bug by forgetting to close the file, or by closing it in one place and thinking it's still open in another. Context managers help with this. Let's use the with keyword in the bottom window to do the same thing. The with keyword can be used with the same open function as above. Seeing as this is a block of code, you get at the file handle using the as keyword along with with. In this case, the open function is returning what's called a context manager, the context in this case being the file's open state. Inside of the with block, the file is open. Once the block is done, the file automatically gets closed, meaning you don't forget to close it. I won't cover it here, but all this magic happens with dunder methods, so like most things in Python, you can write your own classes that take advantage of this feature. Like with above, I read the lines from the file, and here I'll report the state of the file, and then I run the block. Same output as before. But this time, the file got closed automatically. I'm a big fan of context managers, and anytime you're dealing with state-based resources like files, database connections, sockets, and more, the with keyword is the better approach.
So have you experienced something similar in another language like JavaScript where you've left something open accidentally?
So this was a common bug in C. The destructor concept in C++ kind of deals with this as well. So in addition to having a constructor in C++, you also have a destructor, which is a method that can be called once the compiler decides it's out of scope. And so I remember coming across constructor-based ideas that were essentially this. And this is similar to like Python uses, as I mentioned, it uses dunder methods. It's dunder enter and dunder exit.
Yeah.
And so there were smart file libraries out there that were using objects in C++ because of the same thing. So as soon as the object went out of scope, the destructor got called and the destructor would close the file handle for you so that you don't muck it up. So this idea has been around in a few different languages. I don't know that I've seen the with context before,
Okay.
but Python does steal from a whole bunch of places. So if somebody told me it was in Scala or Ada, I wouldn't be terribly surprised.
And have you ever used the enter and exit special dunder methods to, create something unique in your own context manager?
Yeah, I've built a couple of these. It almost always comes down to that sort of resource management thing,
Right.
right? So you want to have something on and then you want it to be off once it's out of scope. When that pattern is showing up in your code,
Yeah.
then, this is a good one. One of my favorite uses of this actually is inside of unit tests.
Yeah.
Sometimes you need to check a failed case. So you want something to raise an exception. Well, in order to test that the exception is raised, that's going to raise an exception. And you could put a try block around it and then put some code in that checks that the exception got raised. But in fact, there is a with method for this, which is with assert raises. So you can essentially say the code underneath this block is supposed to raise an exception. And if it doesn't, it raises an exception. So it's kind of the counter to help you test error handling code. And it's a really, really useful one of these. It actually saves you a whole bunch of extra lines of code.
Yeah, I feel like we're going to see more and more of this under the hood sort of special method stuff that is architecture that you don't necessarily need to, create and edit yourself, but as you become deeper and deeper inside the language and need these sort of hooks, if you will, they're available, which is kind of nice to see that being built out.
Yeah, I think it's one of the powers of Python. So many of the things that the language itself uses are mechanisms that are available to you. So
Right.
that, in other languages, they'd add a keyword and then you'd be screwed because you can't add a keyword. Whereas, Python's default answer to everything is a dunder method. And it's a little
Right.
weird if you've never seen it before, but once you
I
get
didn't
used
like
to
the
it,
name of it originally, that I would always see of magic methods.
yes, yeah. But once you've seen it and you've gotten used to the idea, it's all of a sudden it's like, oh, hey, there's a place where using a less than comparison in my objects makes sense. I should be able to implement it, right? Yeah.
Yeah, totally. Cool.
Okay. Let's try the default dict. So default dict is a special kind of dictionary. In order to explain it, it's a little easier if I show you the case without it. Say you've got a dict that's going to act as a thesaurus. Each entry in the dict maps to a list, in this case, the synonyms of hello. Which means if I want to have something empty inside of it, it has to be an empty list. That way I can use the append on any key that's in there. If you don't start with that empty list, each time you go to use the dict, you'd have to check whether or not the key existed and create that empty list before calling append. That ends up meaning an if-else block each time you added an entry. And of course, this means you have to remember to create that empty list. Or do you? Default dict is in the collections module and helps you take care of this kind of thing. For the most part, it's like a regular dict, except it allows the creation of a default entry. Anytime you do something with a key, the class checks if that key exists, and if it doesn't, it creates the default. In the example here, I'm setting the default value to a list, just like with synonyms above. It's important to note that you pass in the list class, not an empty list. You don't want an instance. You want default dict to create the instance for you. But now I can act as if that empty list was there, even if I haven't created an entry. Because of the default, I can append to something that isn't there, because by referencing it, the default dict creates the list, allowing that append. Examining the class is a little more verbose than a regular dict. You can see what it defaults to and what is currently inside of it. One thing to keep in mind is that any reference causes the default to happen. So by examining a not yet existent key, you actually create the entry as a side effect. This is mostly a good thing, as it's what causes the class to work. It can mean that if you're using this to deal with sparse data structures, you have to be a little careful that you're not accidentally creating empty entries when you don't want one. Like a lot of things in Python, this really only saves a line or two of code, and that, I guess, isn't a really big deal, but it accumulates over time. Every little line or two is one less line you've got to maintain and think about. Have you used these?
I have. I find it useful in lots of ways. Just the idea that, like you said, you don't have to create a bunch of if then else statements sort of stuff to kind of, confirm that this is properly ready to go. Here, I find your person saying hello in this third case a little rude, though. Saying later, dude.
My hello was a goodbye. Yes.
Yeah, exactly.
Oh, those are antonyms. That's why.
Oh, that's right. Okay. Sorry.
It's quite all right. I'm trying to remember. I think like 98% of the time when I do this, it's a list. Like it's almost always this pattern. I'm trying to remember if I've ever used it for anything else. To learn more about functional programming, read this tutorial. Or for context managers, this course and tutorial will help. Earlier, you saw the guitar to denote Mr. Bailey's courses. The 8-ball is for mine. I'll let you guess whether I play billiards or just like hanging out with mystical plastic spheres. Outcome is unknown.
Ask again later.
Ask again later. That's right. The next lesson covers a monumental time in Python history, the 2 to 3 transition. In the previous lesson, we covered the with keyword and default dicts from collections. In this lesson, we'll talk about the 2 to 3 transition and what it meant to go from Python 2.7 to 3.0.
So Python 2.6, which is from 2008 to 2013, introduced the format method for strings, allowing you to kind of go a little bit further than the C-style formatting, adding the curly brackets. And then also exceptions could be caught, if you will, with an except with as statement. And also were added class decorators, building on top of what we already were able to use with function decorators. To learn a little more about raising and handling Python exceptions, we have not only an excellent tutorial, but a video course as well. Python 2.7 had quite the long life. This is about the time that I started looking at Python, and I actually asked some employers, what version of Python are you guys using? It was always kind of a common question around this era, and almost everybody I was speaking to were already working on Python 3, and so that was nice to not have to learn about the differences and how to kind of go into it. So this is kind of a bit of a historical review, which it may be for many of you watching this video course right now. The release actually overlapped 3.0 all the way up to 3.8, and it added some additional things. Not only did we now have the list comprehensions spoken about earlier, but we had dictionary and set comprehensions. Also in Python 2.7, argparse was added to help you work through your command line arguments there, which in some ways was intended to replace optparse. And some of 3.0 and 3.1 features also got backported so that they would function inside of Python 2.7.
Yeah, I almost wish that I had started a little later because
just be 3.0.
2.7 was the only choice when I started. I spent a lot of time and energy shifting to 3. If I'd put off my Python journey by a year or two, I might have made my life easier.
And not like us young people here. Just kidding.
Which leads us to 3. With 3 came a lot of changes. Python 3 was a big shift. Up until now, each of the versions had been backwardly compatible. You could run your 2.2 script in a 2.7 interpreter without any problem, but Python 3 decided to change that. A big justification for that was the move to Unicode. The original Python was ASCII only. Python 2.0 added the U prefix so that you could write Unicode strings, but the underlying code itself still had to be ASCII. Making Python Unicode by default was a big modernization step, but it made compatibility a challenge. And since they were breaking backward compatibility, they decided to fix a few other things as well, because, well, broken is broken. You might as well do a bigger cleanup. One of those changes was to move print from being a statement to a function. This made it more in line with other aspects of the language and removed some complexity from the parser.
So one of the things I've wondered about in this transition from the print statement to the print function is what was missing and what were the benefits of adding it, making it into a function instead of the simpler, if you will, print statement, I feel like.
I don't know what their driver was. I suspect some of it was just, keywords are problematic. The parser has to do special things with them, whereas functions are just functions. So that right there, it might be enough reason to change it.
Right.
This also makes certain things easier. So there was a way with the print statement to, by default, when you say print, it sticks a new line on the end of it.
Yeah.
There was a way with the print statement to stop it from doing that, but it was like this little hackish thing. Whereas the print function, you can specify what the end of line character is. So it made that clearer as well. Fundamentally, I think it was a special case, and it kind of leads you to the question, why? You've got all these built-in functions. Why is print different? And it was there for historic reasons, as far as I can tell. Another change was to switch a number of functions and methods that return lists to things that return iterators. This can actually be a big performance gain. For example, if I call range from 1 to 1,000 with a list, I get the whole thing even if I don't use all of it. With an iterator, if I break out of a for loop partway through, the rest of the form doesn't get generated. This is good for memory and for speed. We'll be touching more on that when we get to the yield and yield from keywords that got added later. Part of that cleanup that I was mentioning was also reorganizing the standard library for consistency. Several modules which had capitalized names got renamed to match the rest of the library with small letters, and several modules got merged together for clarity. For example, URL lib2, URL parse, and robot parse all got put together under the URL lib module. To help with transitioning code, a module named 6 got created. The name comes from 2 times 3, so 2 to 3. There you go. Funny. Programmers can be funny. If you needed your code to run in both Python 2 and 3, you would import 6, and it would map your import to the right place in the interpreter when you were running. So you could say from 6 import Q with the small q, and if you were in 2, it would do the capital for you and figure all that out. So it's a nice little sort of wedge.
I remember when I started seeing this in so many libraries, importing 6 was like such a common thing, and it's starting to disappear.
Yeah, it was pretty much everywhere. You take something, a long-lived library like something like Django, and they've got long-term support standards that are multiple years. So, there were versions of Django that had to be in both the 2 and the 3 world. And you don't want to maintain 2 copies of the code. So you start putting these kinds of little shims in order to try and deal with it.
Yeah.
And along the same lines, the 2 to 3 script was a semi-automatic way of translating your code. You ran it on your Python 2 files and it output Python 3. It wasn't perfect, but it was better than doing it manually. The other change that I want to highlight was the introduction of keyword-only arguments. Before this, any argument to a function could be called by its position or by its keyword. Now, by putting an asterisk in the declaration, any argument after it could only be called with a keyword. So in this example, I couldn't just pass in size. I have to say key equals size, or I get an error. Let's head to the REPL and explore some of the differences between Python's 2 and 3. In the window on top here, I've got a 2.7 interpreter going. I'm going to write a little bit of code, and then I'll do the same in 3 to show you the difference. Python 1 didn't have classes, but somewhere along the way they got added. Nobody was really happy with them, though, so they got redesigned in Python 2.2. Mr. Bailey referred to this as the new style classes to distinguish them from what was the old style class, which, of course, now is both the old style classes, which just is confusing. Anyhow, in order to allow these to exist side by side for a while, the new style classes had to inherit from object, like you see here on the screen. Now I'll add a method and a string. Remember, this is an ASCII string because 2.7, that was the default. By contrast, to get Unicode, with my little patriotic emoji here, I have to have the U prefix in order to get into Unicode mode. And there's that print statement, no parentheses. One more of them, and I'll try it out. And there you go, that's the content. Now let's look at Python 3. Inheriting from object all the time was a pain, especially since the old style objects were gone. Python 3 being a backwardly incompatible release was a perfect time to clean this up. In Python 3, you're still actually inheriting from object, but the compiler is doing it for you. Now my method, and a name, and another flag. Since Python 3 is Unicode by default, no need for the U prefix. And there's the more modern print as a function. There you are, Joe, with your flag to go.
I blame Canada.
Blame Canada. Why not? Python 2.7 with the inheritance from object, because it was a mechanism for allowing backward compatibility. This is something which caused me problems several times. Having come from other programming languages, I didn't always remember that I needed to do this. And of course, if you left it off, you'd get the old style classes, and they didn't behave the same way. And they would work fine until they didn't, because you'd go to do some inheritance or something and it wouldn't work the way you expected it to. So I ran into this trouble a few times. So yeah, it was a dangerous bug because it would work right up until the point it didn't. So yeah, I was very happy to see those gone in 3. So those are 3 key differences from Python 2 and 3. This may not seem like a lot, but if you were managing hundreds of thousands of lines of Python, it could be a lot of work to make sure that nothing broke. And all that work is kind of why the transition didn't go over very well. Breaking backward compatibility caused a lot of work, and coders are busy folks. They want to create new things, not have to do a bunch of stuff just to keep the old things running. The 2 to 3 script I mentioned was helpful, but it wasn't perfect. And this was the pre-vibe coding days. People were suspicious that an automated process would be effective. Folks agreed that some of the changes were needed to modernize the language, but there was a lot of disagreement on whether the amount of work generated was worth the trouble. You'll still see blog posts on how it should have been done, but those are often by folks who weren't actually maintaining the interpreter. The real problem came from it being all or nothing. You were either Python 3 compatible or you weren't, and there was no half pregnant. One of Python's superpowers is the ecosystem. There are tons and tons of libraries out there, and any large code base is going to be dependent on dozens of them. And that's where all or nothing became a problem. Just because you wanted to use Python 3 didn't mean you could, as some library or other that you were dependent on may not have made the transition yet. Large libraries like Django were slow to adopt. The first Django release that supported Python 3 was in 2013. That's 5 years after the Python 3.0 release itself. The transition took a while. Although I lived through this transition, to remind myself on just what the pain points were, I did a bit of digging on the web. I came across a rather typical flame war in the comments section on an article about the transition. Keep in mind, this article was posted after 2.7 was no longer supported, so that's 12 years into the transition, and you still got this kind of vitriol. I miss buggy whips. If you are one of those rare souls who are still maintaining 2.7 code, I do encourage you to read this first tutorial to learn how to migrate. Before exposing you to all this trauma, Mr. Bailey mentioned that 2.7 added argparse. To learn more about that, you can see my course or this tutorial. The next lesson covers how to yield from generators and what it means to mock your tests. The previous lesson covered the 2 to 3 transition. This lesson talks about Python 3.1 through 3.3, the yield from keyword statement, and unit tests mock module.
So moving forward into Python 3.1, which is 2009 into 2012, The ordered dictionary was added. Up to this point, Python dictionaries had always been an unordered collection. So from the collections module, you could import the ordered dict and keep things ordered for your dictionary. And along with that, the counter was added. And by adding a dunder main.py file inside your module, you could run the module just by using its name. In Python 3.2, we've discussed this before, back when we were discussing Python 2. argparse was added, and the idea again to replace opparse. And then going forward, extensions now had a stable application binary interface, or ABI. So all extensions from 3.2 be compatible moving forward. And to continue learning about this more, we have Python's collections, a buffet of specialized data types as a tutorial. So if you want to learn more about the collections modules and the things that were added. And if you'd like to learn a little more about how you would include the dunder main.py file in order to be able to run a module directly, this code conversation that was with Ger Arda and Ian Curry is a really great resource for you. You also learn a lot about constructing your own modules.
Next came Python 3.3. Notice its lifetime here was from 2012 to 2017. That's the first release with a 5-year window. That has become the norm now. The release dates aren't quite consistent yet. That once-a-year thing didn't start until 3.8. Feature-wise, Python 3.3 was the first to include venv for dealing with virtual environments. The solution of virtual environments predates this through the third-party virtualenv library. I remember, Mr. Bailey, you once asking me what I used, and I still use virtualenv, and that's because I was using it before there were other tools, and I'm an old man stuck in my ways.
There you go.
Oddly, Python 3.3 also added the U prefix for strings. This was purely for backward compatibility. If your script needed to run in both Python 2 and 3, you no longer needed to do fancy things to deal with those Unicode strings. You could just use the U prefix again. You might recall that Python 2.2 added generators, and with them the corresponding yield keyword. Yielding from something that yields was a bit problematic though, so yield from got added to deal with exactly this challenge. There are lots of things in this release that I use all the time. Another feature that I like was the introduction of the mock module. It allows you to fake certain behaviors out when running tests. Rather than explain more, how about some examples? Let's look at yield from and mock in the REPL. To better understand yield from, let's go through this step by step, starting with a list, then turning it into a generator. I'm declaring a function, and this function returns a list by calculating a comprehension containing the double of each of the items in the function's argument. Now if I run it, no surprises here. Back when I introduced Python 3.0, I mentioned that a bunch of the functions that returned lists got changed to return generators instead. This makes them use less memory, and if you don't end up consuming the whole thing, it can be faster as well. To see how this works, I'll write a similar function that uses the generator syntax instead. This time I'm tripling, looping through the iterable that's passed in, and for each item, I'm using the yield keyword. When your interpreter hits this statement, it returns the value in place. So if you loop over the return result from this function, each value gets yielded into the iterator. That means you don't need the whole result in memory, and if things get cut short, you don't waste any time creating the other values. Let me run this. If you're not used to this, it looks a little weird. Since generators are only meant to be interacted with, you get back a generator object rather than the values inside of it. That's kind of the whole point. To actually run it, you either have to use it in a loop, or you can pass it to the list constructor. The list constructor takes an iterable, which in this case iterates over all of our generated values and puts them in the list. Okay, so that's generators and yield. Remember those functions that used to return lists and now return generators, like range? What if you want to use one of them with yield? It's a function that counts down from a value, and I'm yielding the range function. I'm going to run it. Makes me kind of hopeful. And then when you convert it to a list, that hope evaporates. This is the worst kind of problem. There's no exception, just the wrong thing got put in the list. So instead of getting the values, you get a reference to range's own generator. Not really helpful. I'm sure you're 2 steps ahead of me. This problem is why yield from exists. Let me redo countdown. Instead of yielding to range, I yield from instead. And this time it worked. This example's a bit of a simplification, as you likely won't need to yield from range, but if you are writing more complex generators where one generator calls another, yield from prevents you from having to do funky things to get them to expand out. Before explaining mock, let me show you the problem that it solves. Say you've got a function that returns true if today is Friday the 13th. Import the datetime module, which is how I'll figure out what today is. Define the function. Get the current day. For clarity's sake, I'm going to print it out as well. And here's my comparison. Weekday 0 is Monday, so I check if weekday is 4, meaning Friday, and if the day is the 13th. If it is, this will return true. Let me try it out. And nope, not Friday the 13th. Now, how can you test this function? Well, you could wait for a Friday the 13th to make sure it works, or you could use mock. What mock does is it allows you to fake out what the today function returns. There are several different tools for this kind of faking out stuff in the mock module in unit test. For this case, I'm going to use patch. Patch can be used as a decorator or as a context manager, and it changes the behavior of the code that it wraps. Here, I'm using it as a context manager. There's a lot here, so let's do it a piece at a time. The first argument to patch is what is being replaced. Note the dunder main. This is different than the dunder main that Mr. Bailey was talking about earlier, which is a file. This is the dunder main, which is the module name. Because I'm in the REPL, that's actually what the default module is. If it were in a script, here, instead of dunder main, you would use the name of the script. The second argument to patch indicates what module is being patched. This isn't always necessary, but datetime isn't pure Python, it's C code underneath, so without this part, it's not going to work properly. And since I'm using patch as a context manager, what gets put in my as clause here is a mocked version of the object. I'm still not quite there yet, just having mock isn't good enough. To test our code, I need to make the mock do something. You can arbitrarily add attributes to a mocked object. So here I've added both a date object and then a today object. So my mock date time is a mock of the module. It has a pretend fake date, which is inside the module, and then a pretend function today inside of that. This allows me to supplant the real today function, and then the return value attribute in a mock tells the object to return this value when the fake function gets called. With today mocked out, any call to it inside of the context block will return Friday, February 13th, 2026. Inside my test, I'm going to call the actual function. And that's it. There you go. Our function works. This is a bit messy, and it can be a little fiddly to get the thing patched correctly, but it's really, really powerful when testing. Does your code connect over the network to a system you can't control? Mock it out. Is your code reliant on anything with a date or time? Mock it out. Are you trying to run a smoke test on a wrapper library that calls something that takes a really long time? Mock it out for performance reasons, then test the underlying code elsewhere. There's lots of good uses here.
And one of the important things you're doing with that is including it in that context manager.
That's right. Because this is unit test, 99 times out of 100, you're going to be doing this inside of some test code. You usually aren't going to use it in normal code because you're essentially mucking with the behavior of things, which you don't typically want to do. I find this is one of those things I have to look up every single time. Like I quite honestly, it took me about 10 minutes to get the right form of this to work with date time. So there's a little bit of Googling involved, but because you're not actually mocking the module itself, you're mocking where it loads the module. That's one of those things that sometimes takes a little bit of trial and error till you get it right. Yeah, it is a little fiddly, but it's really, really powerful. I've only scratched the surface of mock. There's a real Python course and tutorial if you want to learn more. Same goes with generators. This course and tutorial cover a lot, but it actually doesn't touch yield from. But if you haven't done generators before, this might be the place to start. And this is a course on a lot more than just generators, but it does have a section on that yield from piece. So if you want to learn more about iterators and iterables, there's great stuff in here. Or if you're just interested in the yield from piece, go look for that subsection in the course. In the next lesson, you'll learn about enums and how to use pathlib.